Okay, this is the TSP lecture on the two-opt heuristic. So you should have downloaded the code in the zip file and unzipped it. And we'll be working in the starter folder, and we'll do two-opt. Okay. So you'll see here that I've already given you a starting point. So we already have our 20 city graph, the positions of the nodes that are chosen randomly, and then also this code that calculates the distance between pairs of nodes and stores that as an attribute, the length of the edge. Okay. So the way that this two-opt heuristic works is it starts with really any feasible tour. So if I wanted to, I could just pick the tour that just goes node 0 to node 1 to node 2 all the way to n-1, which Python, I could do this pretty easily. So I'll say, just take that list of nodes, and I'll just put that into a list. And if I was interested, I could draw the edges or retrieve the edges by looking at each in the tour and the node that comes after it in the tour. So I could do, for example, range in here because my nodes are numbered based off of that. So if I ran that, this tour, well, if I wanted to print this, so the tour is just kind of this trivial tour, and then the edges of the tour are just every pair of consecutive nodes. Okay, but if I wanted to draw this in our instance here, I could do nx.draw, and I want to draw not G, but the edge-induced subgraph coming from the tour edges. And I want to make sure that I place the nodes based on the positions that we've chosen up here. Okay. So this is our initial tour. This is obviously a really bad tour. Snakes all over the place. And so what we're going to consider doing in two-opt is we're going to repeatedly take two edges of this tour, delete them, and then try to figure out how to reconnect the two paths that result. And hopefully, by deleting two edges and then adding back two other edges, this will still give us a tour and hopefully find something that's shorter than our previous tour. And we'll just do this over and over and over again. Okay. So anytime that we're looking at the nodes in a tour, well, if we're looking at the edges of a tour, one edge will be of this form. So going from the ith position to the ith plus 1th position. So that will be one of our edges. And another edge will be just like that, but with, let's say, j. So when we're looping over, checking every pair of edges in our tour, really what we can do is just loop over the values of I and the values of j, which you can think of as like the tails of these two edges. So I'll loop over all choices of I, all choices of j. And I should probably, if I can make this assumption that this edge right here is coming after this edge in the tour, which I can achieve by making sure that j doesn't start the smallest values. It must only start after I. Okay. So the I and j correspond to two edges of my tour. So it corresponds to that edge, and then the second edge, this one. I can delete that now. Okay. So we're going to consider to drop these two edges from the tour. And when I do drop them, I need to figure out how I could reconnect them, reconnect this into a tour. But maybe I do want that back again. Or maybe let's consider a concrete example. So suppose my tour starts off like that. And I consider two edges from this tour. Suppose one of the edges is, I don't know, 3, 4. And another edge is 6, 7. Okay. But deleting these two edges gives something kind of like this. But I don't have 3, 4 anymore. And I have 6, 7. So really, this ends up becoming, I've kind of split up the tour in two parts. There's this part that kind of goes 7, 8, 9, all the way back to 0, 1, 2, 3. And there's the other part of the tour that's 4, 5, 6. Okay. So if I were to consider adding some edges back to make this into a tour, there's really only one choice for which edges should be added back. And this should be edges, I guess 3 needs to be connected to something. Needs to be connected to something, and I don't want to connect it to 4, because if I did, then I'd just be getting essentially that same tour that I just tried to move away from. And I also don't want to connect 3 to node 7, because if I did, then I'd have this subtour that would go essentially 7, 8, 9, 0, 1, 2, 3, and then back to 7. And then this 4, 5, 6 would end up being its own subtour as well. So really the only choice I have is to connect 3 to 6. And then if I did that, then 4 and 7 need to be touching. Okay. This would end up giving a new tour where, let's say I start off 0, 1, 2, 3, and then 3 goes to 6. And then in this tour that I've broken up, 6 goes to 5, 5 goes to 4, and then I have this new edge 4, 7. And then this continues like it did up before. 7, 8, 9. And then it will, of course, go back to 0. Okay. So you'll see that when I did this, this portion reversed. So this will be important. Okay. So the generally speaking, the two edges that we will consider adding the new 1 and new 2. 1 goes from tour I to this one, which is tour J. And then this other edge goes from tour I+1 to tour J+1. Okay. So then I can compare essentially these two edges that I'm dropping, compare their costs to the two edges that I'm considering to add. So the current length of those two edges is g dot edges 1. What is its length? Plus that same thing for the current edge 2. And the new length is similar, but it is new 1 and new 2. Okay. So if that new length, the length of those two edges is strictly less than the length of the current edges, then I've found an improving move, and I'll want to proceed with this swap. So I will swap edges current 1 and current 2 with the new edges, new 1 and new 2. Okay. And it turns out I can code this quite concisely in Python. So really all I need to do in my tour is I take that 4, 5, 6 part and I'm essentially just reversing it. So everything else stays the same. So really all I have to do is reverse kind of a portion or a slice of this Python list. And I'll say this one I had to look up how to do a little bit of Googling. I found out I could do it like this. So what this says is I take that portion, that slice of my list, which is this part, 4, 5, 6, and I replace it with that same portion, but with this. So this little part right there reverses the list. So that's all this line of code is doing, is just taking this part and reverses it. Okay. Could do this, and maybe it'd be interesting to know what this tour looks like after I make the swap. So I could go ahead and again draw the edge-induced subgraph for those tour edges. Again, using those positions from earlier. I could run this code if I wanted to. This will just repeatedly make those swaps. Oh, this should have been a colon. Okay. Something I did it does not like. So I think what's going on here is right here, this j+1. So this j is going all the way up until n-1. And so this particular case where j is when j is n-1, then this term right here ends up becoming n. So that nth position is longer than this list actually is, but it's really supposed to kind of correspond to kind of what's right here in the tour, the next one after 9, but that really it should just go back to 0. So what I can do here is take whatever that value is and take it mod in the number of nodes. So basically, when you take this thing and you divide it by n, what is the remainder? So if I were to take, let's say, I don't know, 1 mod 20, it would just give me 1 back again. So if you divide 1 by 20, you get 0 with a remainder of 1. If I did, let's say 10 mod 20, then again, 10 divided by 20, it's still 0 with a remainder of 10. But that case where, the very last case where I did like 20 mod 20, that evenly divides. So that would just be 1 with a 0 remainder. And so that's what this spit back. It would say the 0 is the remainder, and that would essentially point me back to the beginning of the tour. Okay. So I think likewise, I'll need to fix this here. Okay. And maybe I should point out each time that it swaps edges, takes 2 of them, deletes them, and adds back 2 new edges, it draws this graph. But I think the way that Python is working here is it's essentially drawing these graphs one on top of each other. So to make sure that it's actually showing me a different graph for each one of these iterations, I need to do something. I can do this plt.figure, and then I need to define this plt. So I need to import dot as plt. Okay, so you'll see now it will swap an edge or swap 2 edges and then draw it again. But if you look at this last tour that it drew, this one's still really bad. And so what's going on here is that I've only done one pass. So I looked at all values of I and all values of j, considered swapping those edges. And then at the end, it just returns whatever I found. But if at any point during this loop over I and this loop over j, if I ever improved my solution, if I improved my tour, it's possible that maybe there's still another improving move, but I just have to go back again to maybe the same value of I and the same value of j in the tour. So really what I want to do is anytime I am successful and make a swap, I really want to go back and do all of this all over again. So what I'll do is I'll define this variable. It will be a Boolean variable, which will initially be true. And it's going to keep track of, do I ever make an improving move? And if I do, I'll just repeat. So while improved this, and if I just left it like this, it's just going to be in an infinite loop. At a certain point, it's not going to have any improving moves, but it'll still keep trying. So I need to make sure that anytime I enter this loop, I set this flag to false. And then I guess if I did this, it would just do 1 pass. So I need to make sure that anytime that I actually do make this improving move, I need to update this thing and say, yeah, it improved. Okay, so let's give that a go. So that may have been locally optimal. Let me rerun some of these things. So maybe I'll just restart and run all. See what happens. Okay, so you'll see it's making a lot of edge swaps. And the tours, let's see if they're looking any better as I go down. Still looks kind of bad. Huh. Okay, that still looks really bad. So apparently I've done something wrong here. Oh, I think I see what I did. Actually, I'm not sure. Oh, I think I know. I think it's not, these pictures are all the same. So tour is changing, but every time I'm drawing that same set of tour edges. So what I need to do is update tour edges in every iteration. So I'll kind of copy this code. After I get the tour, I'll get the tour edges, and then I'll draw that new set of tour edges. Okay, let me restart, run again. Okay, so making a lot of edge swaps. So let's hope now that the pictures are starting to look prettier. Getting there. Okay, it looks a little better. Okay, so that shows you all of these iterations, and then maybe what I could do at the very end is to just again. Okay, so there's our final tour for 2-opt. So this tour is so-called locally optimal in the sense that if you were to ever try to delete 2 of the edges and add back those other 2 edges, it would never improve the objective. Now, this does not mean that this tour is globally optimal, that it's as small as it possibly could be, but at least with respect to those kind of 2-opt local search moves, you can't do any. From this point right here, you can't get to such an improved, a better tour using just those 2-opt moves. Okay. I think in practice, this is probably a pretty good solution. I will stop here.